Hi class, welcome to our discussion of groundwater velocities and groundwater discharge. In particular, we're going to focus on what is essentially different forms of something called Darcy's Law in these discussions and how to calculate and to set up problems and solve problems using Darcy's Law. The basic equation is shown here. In this case, we're focusing on velocity. In other cases, that means we're dealing with distance over time, but in some cases we'll be doing discharge, which means we'll be doing volume divided by time. Velocity is equal to K, which is hydraulic conductivity. That's a parameter related to the aquifer, how water moves through it. Porosity, the volume of water in the system, times change in h, which is the height, or really h is the elevation, divided by the change in distance between 2 points. Okay, those 2 points might be wells in the case of this problem down here. So I want to talk about this problem and the problem below it. The first is to calculate the groundwater velocity using this equation in centimeters per second, and then the second will be useful just to show you how to convert to different units. So here we're in centimeters per second, and here we're going to be in meters per year. Okay. If I switch to the next page, I'm going to show you what it looks like when I set the problem up, and I'll just walk you through it. This short little sketch here, this small sketch, we have the ground surface here, we have the water level here. So this is the unsaturated zone, and this is the saturated zone down here. We have an elevation for the water table here of 813 feet, and an elevation for the water table here of 574 feet. I'll scoot this over a little bit. Okay, and so these are given as part of the problem, these elevations. And we want to know what the velocity of groundwater is as it flows from high elevation, or high head, to low head. Okay, and we're calculating that velocity using this basic equation that we looked at in the previous page. These other two parameters here are for the actual sediments or rock that make up the saturated zone: hydraulic conductivity and porosity, which are given in the problem. And so using these four terms, we can calculate the velocity as water flows from well 1 to well 2. Okay, so let's take a look at the units. We've got hydraulic conductivity, 5.0 times 10 to the negative 3. Elevation, 813, 574 for a second elevation. Distance between those two is going to be 0.5 kilometers, and 24% for porosity. So this problem, if I was to write it out, will kind of look like this. Set up, and I might zoom in just a little bit. Might help make things look a little clearer for us. Velocity is equal to 0.005 centimeters per second divided by 0.24. So I converted the percentage to a decimal here, and I simplified this and got rid of scientific notation, times 813 meters minus 574. So these are both elevations, right? Well 1, well 2, we're subtracting because we want the change. And then down here, or over here, it says delta L. You really could just put distance. L is just distance. And the distance between those two wells is half a kilometer, so that's 500 meters. Okay? Simplify this expression, dividing through, and we get velocity is equal to 0.021 centimeters per second times this term. Now meters are going to cancel here, and we're going to end up with a unitless value, 0.478, okay, is equal to 0.01 centimeters per second. All right, and that's the answer. That's the groundwater velocity given these terms from well A to well B, given the gradient or the change in elevation, which we talk about on most topographic maps. We've talked about this as part of the problem for calculating how steep a slope is, right? Same concept. If we want to convert this, I'm going to do this in one big long set of steps and write it all out for you. 0.010 centimeters per second. I want to convert that to meters, and I'm going to do distance and I'm going to do time in separate. So it's in centimeters. I'm going to go centimeters per second. I'm going to need to convert it into meters per year. I'm going to do distance and time in different sections. So here's meters, and I know I've got 100 centimeters per meter. So what that does is it allows me to cancel here and cancel here. I'm going to leave that there. I'm not going to do any multiplication. Now I'm going to deal with time. So this is distance first. Now I'm going to do a time over here. The next set times 60 seconds per 1 minute. Right, so now I've just gotten rid of seconds, so those cancel them into minutes. Times 60 minutes per 1 hour. Okay, minutes are going to cancel here and here. I'm down to per hour. I'm going to go times 24 hours per 1 day. Hours cancel them into days, and now I'm one more 365 days per 1 year. I've finally got to the year part, right? So centimeters cancel, I'm at meters. I'm now at years here, and that whole answer is going to be 3,153.6 meters per year. Okay, so you multiply this whole through, multiply through, so it then becomes 0.010 times, divided by 100, okay, or times 1 over 100, depending on how you want to think about it, times 60 times 60 times 24 times 365 is going to give you this value. Okay? So I've separated this out, but I've written it all as one complete problem.